Right. So to balance an equation, we are doing so because we need to meet what is known as the law of conservation of matter. And I'm going to show you kind of like a proof of that with a very simple equation. So I'm going to start sharing. Okay. Okay, so let's look at balance versus not balance. And I'm just going to go ahead and type it in with a text. All right, so basically it's H2, and I cannot do lower, subscripts on this one. So you're just going to have to bear with the non-subscript look.
Okay.
Okay, so that's making of water. All right, so every single mole of H2 weighs whatever one atom of H2 says it weighs, not one atom, but one mole actually of H2 weighs in the periodic table, which is 1.01. So since we have 2, it's going to be 2.02. I'm just going to do this fast. All right, so that's the first, right? 2.02. And then we have oxygen, which in the periodic table is 16, right? So times 2 is 32. All right, and that should be equal, right? Because according to the law of conservation of matter, that's how it should be. Again, to 2.02 because we have, 2.02 because we have two hydrogens, but we only have one oxygen on that side, right? So if you look at this, that would be 34.02, right? It's not equal to 18.02. See? This is a false statement, but I don't know how to put not equal other than to use my little pen. Right. Not equal, right?
Right.
All right, so let's look at the other side. When we balance, okay, so the same equation, H2, capital H, 2 plus, I'm going to give some space so we can put stuff on there. O2 yields, and that's H2O. Okay, so if we are looking at this without balancing, we need to always look at the most complicated one first, which I highlighted, and compare it to the rest. And as you can see, there's only one oxygen on this side, so we need to put a 2 there, which makes us now put a 2 in front of this hydrogen, right? Okay, so now let's see, that's balanced. Now let's see if the math works. Okay, so 2 times 2.02 is 4.04, right? And then we still got 16 times 2, which is 32. That should be equal to, all right, we can do this 2 ways. We can say 2 times, we know that 1 molecule of water is 18.02, like, from the other side, right? Okay. And as you know, this is 36.04, right? When we add it, and is that equal to, that is 36.04 also. Look at that. You see that? Right. See why it's necessary to balance equations?
Right.
This shows you right here that it is very necessary because it is the law of conservation of matter. It says nothing can be created, no matter can be created or destroyed, only transformed. So this doesn't prove that this side, the left side, does not prove the law of matter right here, the law of conservation, because it didn't conserve it at all. That's because it's not balanced. Right. But on this side, it did conserve exactly the same amount. So it just transformed it into water, but it's still the same amount of matter or mass. Okay. All right. So let's share this other PowerPoint. Oh, not you. I did not say you. I want to share you. Okay, can you see that?
Uh-huh.
The PowerPoint? Okay, so there's a balancing equations PowerPoint. This one I mainly use for one purpose, is to look at the difference of terminology. I know it's got a lot of explosion. All right, so this is how molecules are symbolized. So if you're looking at Cl2, what you're meaning is you have two atoms of Cl or chlorine bonded together, like this.
Mm-hmm.
With a 2 in front of it and a Cl single, that what it means is you have two atoms of chlorine, but not bonded. You see that?
Mm-hmm.
And the next one just means to have two of the first. See?
Right.
So anything in front of it makes it double or triple or quadruple or whatever you put in front of it, right? In front, the big number, that is called a coefficient. You can see this okay?
Yes, ma'am.
Because it says my screen sharing is paused. Oh, I guess it must be the other one. Okay. All right, so that is exactly what you want to look at. So to see if we have understood this, remember, a group of atoms such as a polyatomic ion, this number down here, which is known as a, let me just get rid of this thing so I don't come back to it. Yeah, let's just get rid of that one. See, that's why it went away. It's because it was pausing. Oh, it didn't even go away. Stupid thing. Why are you doing this? Oh, this is so.
It just keep going in and out on my side now.
I know. Okay, now I'm going to do it. There we go. There we go. Now I can see that I'm sharing this.
It's
All
back
right.
up now.
So like I said, a group of atoms such as a polyatomic ion, like this one, OH, just means that you have, and this two means you have two of those bonded to the calcium. You see, like this.
Right.
All right. So if you put a 2 in front of this, it's multiplying all of that. Okay. So whatever's in front, not separated by the plus. Okay. Because the plus always tells you that's something new.
Right.
All right, so let's look at what this symbolism really means right here. Okay, so how many atoms are in each of the following? And I want you to tell me each of atoms of each. Okay, so here you have what?
2.
1 atom of sodium, 1 atom of hydrogen, and 1 atom of oxygen, right?
Okay, yeah.
Okay, here you have what?
You got 4?
Well, you have 1 atom of calcium, and then you have 1 atom times 2, right? So 2 atoms of oxygen and 2 atoms of hydrogen.
Okay.
And then this one, see, is triple that, right?
Right.
So it's going to be 3 atoms of calcium, 6 oxygen, and 6 of hydrogen, you see? So that 3 in front is multiplying all of it.
Right.
This 2 right here is just multiplying what's in the parentheses. And that's what you gotta learn to look at, because otherwise you'll never balance anything correctly. So this 2 is just multiplying what's inside the parentheses. This 2 is multiplying that, yes, but this is multiplying all of it.
Right.
So that basically is telling me that there are 6 OHs. You see that? Okay. All right, so let's look at balancing now. All right, so my tips, oh, and this is important too, right here. Go ahead and take a picture of this thing. This is the activity series of metals on the left, on the right. And the reason it matters is because when you have a single displacement reaction, which we will look at in a minute, the ones that are above will replace the ones below, but not the ones below replace the ones above. So like, for example, right here, iron is above copper. You see that? And iron is the lonely one. So the one being replaced, which is copper, has to be lower than the one that is replacing it. Okay? And you notice iron over here is much higher than copper, right? That means it's more reactive. See, copper is way down here. All right? So this reaction would happen because of that. And then we just kind of go with the actual reactions. Okay, now look at nickel and sodium. Sorry. Look at the yawn. Nickel and sodium. So nickel down here, sodium way up here. Who's alone? Nickel. Nickel is not going to replace something that's higher, and it's already bonded. You see that? So this reaction will not happen. Aluminum and copper. Okay, aluminum up here in the pink, and copper down here in the white. Well, white, no color. Actually, that's more like tan. All right, so that will happen. Lithium and zinc. Lithium's up here, zinc is down here. So yes, it will happen because lithium's the lonely one. Whatever's alone, not bonded, right, has to be higher than what's inside the molecule. All right, and lithium and hydrogen. Lithium's up here, hydrogen's way down there. So yes, it will happen. And then this is just another reaction. That's called the ACE synthesis reaction, but we'll look at it later. All right, so the very first one we said, oop, I always forget. I saved it. Yeah, I have to fix this. I have to fix this one. It doesn't do well if I don't fix it. If I don't fix it, it just kind of jumps on top of each other. Oh, that's not you. That's the wrong one. I need you. You. Yes, you. Okay. There we go. I need to enable editing and then just stretch it. I don't know why on earth it keeps doing that, you know, because it's not. I mean, it's like I don't fix it every time, and I do, but it is the way it is. Okay, there we go. All right, so now let's just share again. Put it back on and share, because I know I'm not sharing yet, am I? I need to share.
Nope.
Because it stopped sharing. Yeah, I know. When I got off, it stopped sharing, and that's not how it supposed to be. Okay, share. All right, now you can see it. Okay, so we were saying, and we already balanced, but don't look at that. Close your eyes. I'm just kidding. All right, so there you go. So these are the ones we looked at. Now, the first one, the copper got pushed out of the compound and so iron took its place. Okay, this is what is known as a single replacement. Nickel will not happen because nickel's lower than sodium. Aluminum and copper, yes. Lithium and zinc, yes. Lithium and water, yes. And aluminum and oxygen, yes. Okay, so all of those work. Now, to balance, this is my tip to you. Always look at the most complicated one first. So I'm going to annotate here. And this is one of the things that I have come across through so many years of doing this. Okay, so look at this. This is the one that has the most atoms, the most complicated of all. And look at, compare it against what's there, okay? So that one doesn't need alteration because this is higher. What about this one? Nope, it doesn't need alteration either, does it?
Nope.
Okay, so, but we can tell that there's a 3 SO4s here and there's only one here. So we can start here with a 3 there. You see that? Because that gives us 3 sulfates. and 3 coppers. Now we need to balance the copper, which is here. And then obviously irons, we have 2, so we need to put 2 right there. See how we compared the most complicated against the others?
Mm-hmm.
That's what you need to do. All right, so I'm gonna erase these arrows because I'm gonna have to make new arrows. All right, so the next one is no reaction, so we can't balance it because nothing happened. But the next one that we have is this copper chloride. This one actually has more atoms. So we're going to compare it against the others. Okay, you notice that the chlorine over here is a 3, here is a 2.
Mm-hmm.
You can't have something odd against something even unless you make the odd even.
Right.
And that means put a 2 right there, right?
Mm-hmm.
And that 2, don't look at the aluminum yet because you still got to finish balancing the thing that we looked at the arrow against. You notice your chlorines here, you have 6 now, so you need a 3 here, right? Right? Oh, come on.
Mm-hmm.
That 3 is the ugliest 3 I've ever seen. Oh my God, what was that? Okay, there we go. 3. All right. So you can see now, you can now balance the copper and the other one. It doesn't matter. The aluminum is just 1, right? So you can just put a 1 there, or you can just leave it blank. You notice I didn't put 1s, but I think in your connect, they want you to put a 1.
Mm-hmm.
Just so that they know you didn't just leave it blank, you know?
Right.
So that's what we're doing it here, but we don't really have to. Okay, here again, we're going to have to compare the lithium. Okay, so according to this is balanced.
Mm-hmm.
The CO3, the zinc
Mm-hmm.
is actually balanced. The only one that's not balanced is the lithium. You see that?
Right.
So you just need a 2 right there. That's it. This one's a little more complicated because the hydrogen has split. When the hydrogen splits, you have to remember that they're not together and you can't count them as together. Over here, they're together, right here, right?
Mm-hmm.
But not right here. So the first thing we're going to do is inspect this guy because it's the one with the most different types of atoms. It has actually all of them. So whatever you do to this matters to everybody.
Right.
Okay, so the oxygen is balanced, but the hydrogen is odd. If you add it to this, it's odd. So what did I tell you? Put a 2 in front of it, right?
Mm-hmm.
Right, because that one makes it even. Now the
Right.
next more complicated would be this one. So we're attacking that one next. All right, look at how many hydrogens we have. We have 2 from the lithium hydroxide and 2 more. So that's 4. So that means we need a 2 right here.
Right.
And see, we had oxygens too also, so we could have just gone with the oxygen. And then we have 2.
I put a 2 in front of the lithium.
Yep, and there you go. That's how you balance. All right, look at this next one. We always look at this one and compare back. So let's compare it this way, right? Look what you see. You see in the oxygen is even here and it's odd here. So again, always put that 2 in front first. See how that modified the aluminum? Now you have 4. You see that? And you have
Right.
the oxygens here. See?
So they put a 3, yeah.
And that balanced it. But you always should look and inspect. This is what I call the inspection method. We'll learn the other method only because some people really like it, but I don't.
Right.
I don't like the other method. I like this one. This is my favorite. Okay, so basically all of these reactions are single displacement except for this one right here.
Mm-hmm.
And this is a synthesis. And that is because 2 elements are being put together into one product. You see that?
Mm-hmm.
And we'll look at more of those later. All right, so another, this whole PowerPoint has a lot more, okay? A lot more. And we're not gonna do all of these because There's no need, but it does have quite a few more. So if you wanted to keep going, you could.
Okay.
And there's like, see, I'm just going to show you the answers. See, they're actually there, all just like I did them. Okay, see, there's more, blah, 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 blah. And see, they're showing you more visuals here for the visual people. You can see that's not balanced. You see two pink things on one side and only one on the other, right? So you know you need to put a 2 in front of that.
Right.
Yeah, and that's how it works. So to balance it, there you go. That is correct. Now, let me show you the non-correct things, because there are things that are not correct. So that is correct. All your coefficients, which is that big number in front of the elements, are whole, number one. That is incorrect because you notice how I put just half? You can't have half. You cannot put a half.
Right.
And that is incorrect because you're playing God. You made MG bond to itself, and you can't do that.
Right.
You cannot change that. You have to stick with what's there. In your first equation, you do not change that. That is untouchable. The only thing you can do is add coefficients. And this is also incorrect. Why is that? Because they're balanced, right? Oops, sorry.
Right.
They're balanced, but they're not to their lowest possible. Look at this. You can divide everybody by 2 and you get 2, 1, 2, which is what we have here, where it's correct. You see that? So that's why. So these are the not to do, okay?
Okay.
These are the things you should never do. All right, now let's go and clean and keep going. All right, so like I said, I'm not going to do this whole thing, but let's do, well, we actually have these somewhere else. See, they're all right here, and you can just balance them yourself on a piece of paper and then check because they give you the answers. Okay, so no problem with those. All right, so we're not doing those. Like I said, don't save it. I say save it, doesn't save it anyway. It doesn't, because I have to replace this one with the one I saved, and I never do.
Okay.
All right, so the first thing we're going to look at, oops, it's not you, nope. Nope, I don't want that one yet. Don't save, nope, I don't want you. We are going to look at the is it balanced practice sheet first. And this is where I do the one I don't like, which I call the inventory method. And it is good for when you first start, so that you can actually become a little bit more aware of what you're doing. But I don't like it because it takes so darn long.
Right.
And you're going to see what I mean. Okay, so let's say this was not balanced. Okay, not balanced. Okay, so let's look. Basically, what you're going to do is you're going to take inventory of both sides. How many potassiums? How many hydrogens? And see, this one I like to do 1 plus 2 because they're separate. This one has 1 and this one has 1. Okay, so it looks like the hydrogen is what we need to attack. And remember, you cannot just attack this hydrogen because that's not going to work. It's the odd number that you have to attack always.
So if it's with this one being the 2 at the end of this hydrogen, so do you add a 2 in front of that?
Yes. You see, no. See, this is what I'm going to show you. All right. Okay. So I highlighted the one that you always should look at. You know, this part doesn't change. You always should look at what you have here.
Right.
And what is not balanced here. What is not balanced is the hydrogen. But you cannot balance the hydrogen without messing everybody else up.
Right.
So if you put a 2 in front of that hydrogen becomes a 2. So does that potassium, and so does that oxygen. You see that?
So then you would have to add a 2 in front of the H2O in the other one.
Correct. A 2 in front of this one. See?
Uh-huh.
And that, and see, then you have to come back in here and say, that's a 4.
Right.
And that's a 2. And now
Okay.
you only think, see, the only thing that's not balanced is your potassium. So if you put a 2 in front of that, then that becomes a 2. And there you go.
Okay.
See? That's how you figure how to balance this way. I don't like it because it's tedious. I think it's annoying. I think it's annoying.
Is this
I don't know.
is
I
this gonna
mean,
be an extra credit piece of work?
I think it's just annoying.
Because it seems like it's a very long progress.
Right? I mean, don't you think that this is
Mhm.
ridiculous? I mean, it's like, why? When you can just do it the other way. All right,
Right.
so let's do this one. We have 1 sodium on this side. What? I didn't want capitals. I wanted tab. 1 sodium on that side. Here we have 1 oxygen, it looks like, right?
Mm-hmm.
And also 1 oxygen here. Here we have 1 hydrogen. Nope, we have 2. 1 plus 1, right?
Mm-hmm.
And on this one, we do have 2. This one, we have 1 chlorine and 1 chlorine. Looks like it was, oops, like it was already balanced. You see that?
Right.
And sometimes they are. And I mean, I could have told you that as soon as I saw it, but that's because I'm used to it.
Right.
You're not, so you don't do
Okay.
it. You can't do it that fast. But you know, that's why we have this little aid. And I'm gonna erase all of these too, because I don't wanna do these like that. I don't like them done that way. We're gonna do them, all of them, the inventory way, which is annoying, but don't remember these numbers. All right, I think that's it. Everybody else? Yeah, okay. All right, so let's do this one. Let's take the inventory again. All right, so I don't like it, but this is what we're doing. So potassium first, right?
Mm-hmm.
Then we have nitrogen. Then we have oxygen. Okay. All right, on this side, we have 1, come on you, 1 potassium. And on this side, we also have 1 potassium. Oops, I said tab, come on. All right, on this side, we have 1 nitrogen. And on this side, we have also 1 nitrogen. On this side, we have 3 oxygens. And on this side, we have 2 plus 2. Ooh, not quite, right?
Right.
Okay, so 2 plus 2 is 4. Guess what? We have to double this one, right? Remember how we said that? We need to make the even odd and the odd even?
So divide the 4 by 2.
Nope, we can't do that. We need
Okay.
to multiply the 3 by 2.
Oh, the 3 by the 2, yeah.
Okay, so
So
put
3 by 2 would be
2
6.
there, and look what changes. The potassium changes to 2, the nitrogen changes to 2, and this changes to 6. Yeah?
Mm-hmm.
Now you can see that we need 2 potassium, so you put the 2 right here, right?
Mm-hmm.
And that makes this potassium change to 2, this nitrogen change to 2, and this oxygen change to 4. And look at that.
Right.
We just balanced it.
Mm-hmm.
Okay. Pretty easy. That one
Mm-hmm.
was. All right. This is a combustion reaction. And this, I have a tip for you. And first of all, you need to learn to recognize a combustion reaction to do the tip, because otherwise it doesn't work. All right, so a combustion reaction always has a type of hydrocarbon, which is hydrogen and carbon. As you can see, this 5 and 4 are the same.
Mm-hmm.
You will always have oxygen in the reactants. Look, oxygen in the reactants on both places, right? Here and here. And the products will always be carbon dioxide and water. You see that?
Mm-hmm.
So that's how you recognize a combustion reaction. So what you need to do with a combustion reaction is pre-check. So what I'm going to do is I'm going to pre-check this number right here, this hydrogen, just the hydrogen. When you divide it by 2, it is an odd number, yes?
Yes.
And see, that odd number would go here, and that produce an odd number of oxygens, which need to be even. You see that? So instead of just doing all of that, just start by checking that and putting a 2. So if this number, when you divide it, is an odd number, put a 2. If it's even like this one, don't worry about it. Right. So now you have the next best thing to do. Oops, sorry. Now let's do the C. We're going to do this thing like it's supposed to be, which I hate, but this is only 3 elements, believe it or not. Isn't that amazing? CH and O. That's it. It looks like a lot more, doesn't it?
They do.
But it's not. Okay, so we started with 2. Sorry. I'm gonna have to do it right. 1. And then this one has 2. Remember, we haven't yet multiplied it at this point when we're looking at it. This one has 2 hydrogens on this side. Oops, too far. And then this one has 2. And this one has 2 plus 1. And this is where you would know what to do. See?
Right.
All right. You would know you have to multiply that one times 2. Right?
Right.
But instead of doing that, I always say pre-check this. And the reason I say that is because then you don't have to do the other stuff, which ends up being a big mess after all. Okay, so if you put a 2 there, that changes this to 4, yes?
Right.
And this to 4 so far, right?
Right.
Okay, so we know we're going to need a 2 in front of that one. And that changes to, no, not a 2. Did I say a 2? I meant a 4. Yeah, and that changes to 4. And this right here changes to 8, yes?
Right.
Okay, so now we have 4 hydrogens. Here we have 2, so we know we need to put a 2 in front of that one. That changes to 4. And this 2 times 1 changes to 2. That equals to 8, no? I mean to 10, sorry. Now, if you divide this by 2, why divide it by 2? Because the other side has already a 2.
Right.
So that gives you 5. So put a 5 in front of there. And there you go. It's balanced. And now you can see that this is 10. You see that?
Right.
Oh, and I forgot to change this one to 4 because I had changed it to 2 and I meant to change it to 4. There you go. All right. So see, this is another one just like it. Another combustion of a hydrocarbon. So if you just check this, like I showed you, just check that one right there. You dividing it by 2 gives you an even number, yes?
Right.
Then you don't have to do anything. All you have to do is put your CHO again. And like I said, I don't like this part, but I'm going to do it that way because I said I would. And I usually hate this part. It's just, I really do. It's just, I mean, I have to teach it this way because, you know, it is what it is, but not my thing. And this is a 2, right?
Right.
Why on earth did you go down there? 2. Okay. And then on this side, we have what? That's a tab. Not, I was hitting. Oh, God. I've lost all my stuff. Tab. There we go. That's a 1. This one right here is a hydrogen. We only have 2, right? And then this one right here, we have a 2 plus 1. Okay. So I usually like to start with the carbon dioxide, but it doesn't matter which one you start with. It's only because it's right there.
Mm-hmm.
All right, so we put a 4 here, and that changes this to 4 and changes this one, right, to 8, because this is the one we're looking at. All right, then the hydrogen, we have 8. Well, we have a 2 already, so this must be a 4, right?
Right.
So obviously that becomes 8. All right, so far, one thing we haven't finished, this one, change to 4 to 4 here, right?
Right.
So 8 plus 4 equals?
Well,
Divided by 2.
6.
There you go. And that goes to 6 here, and this becomes a 12. See?
Mm-hmm.
And there it is, balanced. So it makes it faster when you do it like that. I like my other method better, but we're going to stick to this. I'm committed. I'm going to be committed if I keep doing this. I don't like this. I really don't. All right. So again, 1 on this side, 1 on that side, 2 on this side, only 1 on this side, right?
Mm-hmm.
All right. So it's obvious we need to multiply this times 2, which makes this 2 and makes this 2. And now we know we need to multiply this times 2, which makes this 2. Okay. And this one, it's so many elements. Okay. And it is on the low end of things. That's weird. Okay. So we have silver.
Mm-hmm.
We have nitrate. And this is a tip. If the item that you're looking at survived the reaction unharmed,
Mm-hmm.
it's a group. See? So we're going to call it NO3.
Right.
N and then O. No, it's NO3. All right, the next one. Okay, we have sodium. And the last one we have is chlorine, right?
Mm-hmm.
Okay, so on this side we have, why do you get small every time? 1. On this side we also have 1. On this side we have 1. And on this side we have 1. 1 on this side. I think you know what's about to happen. Don't you? Oops.
I think so.
Yeah, it's balanced.
Yeah.
See?
Yeah.
It's very obviously balanced. Okay, so there you go. Nothing to change.
Yeah, that's true.
And yeah. Okay, so that's how we do these. I'm gonna save this one as is because we're gonna come back to it. Now we're actually gonna balance my way.
Okay.
This is I think it's better. I just think it is. I mean, you may not, but, and like I said, I'm giving you a choice. I just showed you one way. That's called the inventory method that you just did. And I'm going to show you now my method, which is known as the inspection method, because all you're doing is inspecting. And I think your brain is developed enough that you can do this part easier.
Mm-hmm.
Seriously. And I'm not being bad or anything. And just when
Right.
you're a kid, you can't do this kind of stuff. But we're all adults. Therefore, it makes it easier. All right. Again, most complicated one, compare. Look at what I see on the end.
Right.
It's a 2, so we need a 2 there. And look at what I see on the H now. We need a 3. There you go, balanced. See how fast?
Right.
Of course, that's because I'm doing it. And I'm used to it. And that's
Right.
the thing. But you'll get used to it by looking at this too. Look, again, look at ClO3. Remember, we're looking at this one, comparing it to the others. O3, O2. There's no way we can balance unless we do what? Double.
We got to put 2.
Yep, we have to put that 2 there because that 2 is telling us now it's even. Therefore,
got to put another
we need 2 there, and we need how many here?
3.
See, I think it's much easier. This one you can choose whichever one you want to balance because one will balance the other. So, okay, so this one, let's say it's this one. We could have chosen NAF too, but let's just choose that one. All right, okay. Look at what you're comparing. You see a Cl2, right? So then we need a 2 right here. And that gives us 2 sodiums. And that gives us 2 of those. And that gives us 2 Fs too. See, that's it. Done. Right. Made it much easier. All right, this is by far the most complicated. Yes? Wouldn't you agree?
I would.
Okay. And I want you to focus on just the green. Right now. Yeah, I'm about to make it green. That's why I'm saying green. Okay, and that's the whole green. I mean, I can't put it in the parentheses for some reason. It won't let me, but okay. So you see that? That's what I'm focusing on right now. What do you see?
Oh, on green. With the 2 and the 3?
Well, actually, there's a 2 that's multiplying that NO3. So that means there's 2 of those, whereas here there's only 1 of those. So you would put a 2 in front of that, right? And that 2, now you have 2 silvers. Therefore, you need 2 silvers on this side. And look, that balanced everybody.
Right.
See, if you had started the other way, you would have never gotten it that quickly. It just doesn't work as well. It sometimes does. Actually, this one you would have, but don't. Try to always do the more complicated ones first, because they have a lot more in common.
Right.
Okay, so we're going to do this one, and not in green. We need it in yellow, because that's our most complicated one, right? Again, let's focus on the green. Oh, look, this one, it actually let me put the parentheses in there. And let's focus on this green. What do you see?
That we need a 3 from the green.
A 3 in front of the green. Okay, so you need a 3 here, right?
Yeah.
All right, how many potassiums is that?
8.
No, it's 3 times 2.
6, I mean, somebody.
Yeah, 6. 6 goes in front of this one, right? Because there's only 1 potassium. All right, look how many bromines we got now. 6 on this side, but how many here? Only 3, right?
We just got 3.
Right. So since we have 6 bromines here, see, this is where we went wrong. I'm going to show you. And this is a possibility that you can go wrong on these.
Okay.
Because if we put a 3 in front, a 2 in front of it, no, never mind, we didn't go wrong. Put a 2 in front of that, right? Because that's 3 bromines, 2 aluminums, so nothing went wrong. It went perfectly. But if you hadn't done this first, you would have said, oh, there's 2 bromines, 3 bromines there, so I'm gonna put a 3 there, and then that gives me 3 potassiums, and then you can't do it. You see that?
Right.
So you would have had to double everybody. And that's the thing. You don't want to do that. You don't want to get into those situations. That's why you want to balance the 2 most complicated ones with each other first.
Right.
Okay. All right. So this one, obviously the most complicated would be this one. But this is that same kind of thing that I told you about. Where to focus.
Large number on that one.
Remember where you focus? There, right? You focus on the H18 because look, it's another combustion reaction. O2, CO2.
So when you try to even it out, you just put the 2 in front to make it make sense.
Okay, wait. 18 divided by 2 is what?
Nah.
See, it doesn't work. So you need a 2. Yes.
Right.
And that 2 gives me 16, right? Carbons.
Right.
I know these are huge numbers, by the way.
They are.
And then that 18, since it's multiplied by 2 already, we can just put the 18 right there, right?
Right.
All right, now look, 18 times 2 is 32.
Mm-hmm.
And I'm just going to put that up here because we don't have the luxury of the inventory we were taking before.
Right.
And then we have 18 oxygens. So it's 32 plus 18 equals?
We got to add that.
Yes, ma'am, because that's how many oxygens you have on this side. See how you have 16?
And so that puts you with 50.
50 divided by 2.
Right, by 2 is 25.
There you go. Now you're balanced.
Mm.
Yeah, I know, huge numbers. That's
Mm-hmm.
because you have a lot of carbons, a lot of hydrogens, so everything has to come up.
Mm.
All right, here's the one that I said, let's not do that one yet. Okay, so again, most complicated is this guy, right?
Right.
Okay, so let's compare. 05, 02. What should we do when we have an odd and an even number?
Ooh. Add a 2.
That's right. Now, we can see that 2 times 2 is 4. So we start with 4 phosphorus.
Mm-hmm.
See that?
Mm-hmm.
And 5 times 2 is 10, divided by 2 is 5. So there's
Right.
5. Yep.
Mm-hmm.
This one, it looks balanced, but it's not.
Mm-hmm.
Look at the silver and look at the oxygen. See, this is where you would go wrong if you balance the silver first, because the silver is all alone. But the oxygen over here is odd. The oxygen over here is even. So we always put a 2 in front of that one to make it even. Now
Right.
look how many silvers you have. 4.
So
You
4.
see? Exactly. You see, if you had started the other way, you would have ended up with 2 silvers, and then you couldn't have balanced the O's. It would have been a mess. It's always good to focus on the one. Oh, and I forgot to highlight you. All right, look at these. All right, this, okay, either one. I'm going to use this one only because it's got more atoms, but then again, it's the same thing. So I'm going to highlight the 2 things I want you to focus on in green. Well, one in green and one in pink, because this is the green, right? The NO3.
Right.
And the other one's the NaOH. The OH part. I want you to focus on that in, okay, let's say pink, but I think pink might make it. Let's make it blue so you can see it better. All right, and then the OH3 in blue also. Okay, now you can kind of see what to do, right? Because you have 3 NO3s, and 3 OHs.
Right.
So which one do you want to start with?
So since the 3 in the green on the end, you put a 3 in front of it.
Yes, we need a 3 there, okay? See, that gave us 3 sodiums, which means we need to put a 3 here. And we had to put a 3 anyway because of the OHs, you see that?
Right.
And see how fast that balanced?
Mm-hmm.
That's because you didn't focus on the N, the O, and the O and the H, and separately. They were a group. And that's why I wanted you to focus on the whole green thing and the
Right.
whole blue thing. Yeah, it makes a big difference. Okay, so now we're going to look at types of chemical reactions
Okay.
because they go beautifully together. All right, so we have 5 types of chemical reactions. The first one that we're going to look at is combustion, and that's the one we've been talking about all along. So it's burning of any substance in oxygen to produce heat. But if you have a hydrocarbon, right, is going to be, the products are always going to be carbon dioxide and water. And this is the key. If you have a normal, a normal metal like magnesium burning in oxygen, you're going to have Mg plus O2 yielding MgO2. No, MgO, sorry, because both of them are 2. So yeah, MgO. So that, see how the products contain oxygen? And there's oxygen in the reactants each time? Okay, the hydrocarbons, that's the carbon and hydrogen compounds. They will form always carbon dioxide and water. Never in the same proportions, obviously, because they're different, but there will always form carbon dioxide and water in the presence of oxygen. So again, that's something to remember. So right here, sodium burning in oxygen becomes sodium oxide. And then you just balance.
Right.
And then hydrocarbon burning in oxygen, you just balance. Okay?
Right.
That's the combustion. That's number 1. Number 2 is synthesis. If you're a visual person, you like the bottom. If you're more abstract, you like the A plus B. If not, you'll like what I'm about to say. You have 2 simpler substances becoming a more complex one. So basically what you're going to have on the left, you're going to have multiple things, right? Separated by pluses, becoming one on the right, which is not separated by a plus because it's all one. All right. So there you go. So one product only. That's the key. And here's an example. Hydrochloric, actually hydrogen chloride, because that's not the acid, that's a gas. And hydrogen and chlorine gas becoming hydrogen chloride gas. And there you go. And if your products are ionic, they will always cancel charges. What does that mean? Remember how we always put compounds together by canceling charges? That's all it's saying. So basically, if you had H2O, for example, that was making like let's say you had come on. Let's say you had I don't like you when you do that. H2 plus O2, right? That's a synthesis, becoming water. You see that? See? And how do I know how to put H2O together? Because O is a -2 and hydrogen is a +1. So we need 2 of these. See? To make the positives and negatives cancel. That's all. That's what it's saying.
Right.
Okay. So, and then the covalent ones, you see how it says? Hard to tell. It's true. It's very hard to tell. Those things, since they can make just about anything, it's hard. It's hard to know what's going to happen. So right here, aluminum and chlorine becoming aluminum chloride. You see? And there's the balancing thing that has to happen because these are not the right ratios. The ratios are going to be Ca, 1 Al for 3 Cls. Over here, we have 1 to 2. So we need to make them even by balancing. That's it. All right. The next one is decomposition. Exactly the opposite of what we just looked at. You have one thing becoming multiple. Okay? So an example is the breakup of water. Exactly the opposite of what I just drew. Look. See? And why are they doubled? Remember that Brinkelhoff that I gave you a while back? That's what these are. All of those elements that are always doubled are bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. See, Brinkelhoff. See how oxygen is double? So is hydrogen. So was bromine in the other one. Yeah, and nitrogen. Yeah, they're always going to be double. In chlorine, yeah, that's how it works. It's how the elements like it.
Right.
Put it that way. All right, so let's keep going to the next one. And okay, so if you have a binary compound, that means all you have is two elements. They're going to break up into those two elements. Okay. If you have other things, they have their own rules, and it is hard to tell what they're going to do depending on what it is. So I can't tell you what is going to happen until I know the rules. So like a hydroxide will make into the metal oxide in hydrogen, for example. See, that's not what that's saying, right? See, it's hard to know. But in this case, KBr, it's a binary. So you're going to get potassium and bromine. And see, there's bromine doubled, just like this one up here. Bromine. And then you just balance. Okay, this one is a little bit different. This one is called single replacement. We saw a bunch of those earlier. Remember that?
Right.
Those reactions where one metal displaced the other? Well, that's exactly what's going on here. See how the A, which is alone, replaced the B, which was inside the compound? And now it is alone. So in order for this to happen, it says it here. It has to be more active. So right here is an actual reaction going on. This is copper right here, and copper is more reactive than than silver. So silver nitrate is in the solution, okay?
Right.
But the copper is actually replacing the silver in the solution and throwing the silver out. That's why you see all these little crystals right here, all these little, like, not crystals, but like long little things. Those are silver, pure silver right there, silver ions being displaced. So that's what you always know. The metal is going to replace a metal, and a non-metal is always going to replace a non-metal. As far as non-metals go, if you look at the periodic table, the halogens, the group 7, they are going to replace each other in the order that they are in the periodic table. In other words, fluorine, which is at the top, is going to replace anything below. But nothing below it can replace anything above, okay? So just like the other one, like right here, iron and copper sulfate. Iron is higher than copper, therefore this reaction will take place. You just got to do balancing. Bromine and chlorine. Bromine is below chlorine. This reaction will not happen. You see that? All right, so the next one is double replacement. This is like switching partners. Basically, the A goes with the B here, and the C goes with the D, but it ends up being the A and the D and the C and the B. You see that? So they're actually switching partners. In order for this to actually happen, this reaction needs to commit. What does that mean? That means one of these products needs to fall out of solution, become a solid, because it is insoluble in water. Therefore, it falls out of solution. And then there's no going back, right? Because it's no longer soluble, therefore the ions aren't there to switch around, like right here, see?
Right.
All right, so over here you have the lead nitrate, right? And here you have the potassium chromate. And when you put them together, you have the potassium chromate, the potassium nitrate, sorry, which is in solution, but the lead chromate, the lead 2 chromate, is not going to be in there. Why? Because it fell out of solution. That's the yellow stuff. See how it's clear behind it? That's because, yeah, it fell out. So all you actually have in there is potassium nitrate in water. That's it. The rest of it is a solid and it's not working. And that's what it's telling you here, see? So basically the products, you're going to switch your negative ions, and one product must be insoluble. And for that, there's a solubility table and you check all that, but that's for later. Okay, right here, lead nitrate, lead 2 nitrate, and potassium iodide are going to happen because potassium iodide and potassium nitrate and lead 2 iodide are soluble.
Right.
See, one is insoluble, the lead. Lead is not very soluble, as you noticed. And then this one right here, both of these are very soluble. So the products are going to keep switching back and forth, back and forth, back and forth. So this reaction will really not happen.
Right.
Because nobody committed to it, in other words, and just kept switching around, right?
Mm-hmm.
Kind of like, you're out of commission when you get married, supposedly. You don't want to be with anybody else. Well, some people don't, but that's what's supposed to be.
Right.
Well, that's your lead iodide right here, lead 2 iodide right here. It actually fell out of solution, no longer available.
Okay.
Okay, so now let's go and see if we can identify these guys from our sheets. Remember the sheets? Aha.
Oh, I don't know what I'd be doing with those sheets.
Well, I have them here. So look, this one right here, okay?
Mm-hmm.
What do you see happening?
Mm-hmm.
What?
Number 3.
Number one.
One.
Mm-hmm. Well, you can't see the cursor, can you? Okay, you see how two single things are becoming one?
Uh-huh.
So this is a synthesis.
Okay.
You see that? Also known as combination. In your book, it'll probably call it combination. But I like to call it synthesis because then I can just abbreviate S.
Right.
Rather than having to put all the synthesis. Oh, sorry, synthesis. There we go. I was like, why you strike through my stuff? All right, so this one, what do you see happening? Okay, the opposite, right?
Right.
One thing is becoming multiple. So this is a decomposition. You see that?
Mm-hmm.
All right, look at this one. What do you see happening here? See how chlorine is in here and fluorine is out there, and now chlorine is out there and fluorine is in here?
So that's a synthesis too?
No, that's a single replacement, because it replaced one thing. Because see, if this isn't bonded to something, how can it replace it, right?
Right.
So it's not double replacement because there's only one thing to be replaced, and that's the chlorine. The chlorine is being replaced by the fluorine. All right, look at the bottom one, the number 4. What do you see there?
Two things bonding.
Two things doing what? Replacing each other?
Uh-huh.
So that's a double. You see that? And that is how you know. It's because if we colored them, okay, we already have the magnesium and the other one colored. Let me just keep going with this color combination that we have.
Mm-hmm.
All right, let's color the silver. Let's make it blue. And let's make the chlorine pink, just because we can. See, the color combinations are exactly opposite now.
Right.
See, you had blue and green and yellow and pink. Now you have blue and pink and yellow and green. See, that kind of helps you look at the double replacement.
Right.
When you look at the color combos. All right, look at this next one. What's it doing?
It looks double too.
It is. Oh, I missed the knee. Okay. And then the next one, this is the one that most people find the hardest. To me, that's the easiest because
It's single.
no, this is a combustion.
Oh, it's a combustion.
Because, okay, so this is the key. Always look for oxygen in the reactants, and the products are always, and I mean always, there's never any other choice, carbon dioxide in water, if you have a hydrocarbon. Okay, see?
Hmm?
So that's what you got to look at. The products are carbon dioxide and water, and you have oxygen in the presence of a hydrocarbon. Hydrocarbons are just carbon and hydrogen. Sometimes they have a little oxygen in them, but that's what a hydrocarbon is. And basically, it's the burning of something. All right, look at this one. What's going on in this one?
Mm. What's going on in this one?
Okay, just look at the elements. Don't look at the numbers. A lot of people have problems with the numbers. Just look at the elements. You have P and O becoming PO, right? Basically, is what you're doing. So this is a synthesis.
No. I mean, a synthesis.
Yeah, synthesis again. Synthesis. Because it's getting together. Look
Right.
at this next one. What's going on in that one?
It decomposed.
Yes, they're divorcing. See? Silver took most of it. I'm just kidding.
Right.
I'm just kidding. Because it's got a 4 in front of it. Decomposition. Oh, you see that? Look, it strikes me out if I don't do it right.
If you don't type it right, it kicks it. Like it puts a line through
Yeah,
it.
annoying. Okay, what about this one?
Mm. It's making a connection.
Okay, so what kind of?
So they make it a double.
Yes, and double replacement with my high school students. We used to have to give them like more visual things to them, so we actually made cartoons. But listen to this is what they call these. Okay, so this was synthesis. They just said they're getting together. So marriage, that's what they called it. They called this marriage. They called this divorce. They called the single displacement a boyfriend stealer. And they called number 9, or this one, they call it the swingers.
My goodness.
That's what they did. And I was like, no, you can't call it that. You have to call it something else. But they're
Right.
supposed partners. I'm like, okay, that's true. They are. And then the
Right.
combustion, they could never get that one. I don't know what it is about the combustion, but they couldn't put it together with anything, so they could not, they never could identify it. It was weird. Not never, but mainly not. All right,
Right.
so that one's done. Now let's not save you. Now let's get the next one, the one we did in the other method. All right. So what's going on in this one?
And that is this is a synthesis.
Not exactly. Look at what's really going on. Look who's moved out, who's moved
Oh,
in. Yeah, it's a
two.
single. No,
Yeah.
single. There's nothing to replace on the other one, right? Because it's by itself. So that's how you know. Okay, this is a single because Potassium over here is lonely, right?
Right.
Over here. And so is hydrogen over here, see?
Right.
So that's how you know. They booted him out. That's the boyfriend stealer. These kids, I'm telling you. All right, so here, this one is a what?
This one is combining.
Mm-mm,
No, it's
no.
not combining.
Look at where the chlorine is. Look at where the hydrogen is. See, that's a double.
So that's a double.
Mhm. This one's a little harder to tell because it formed water, and most people don't realize that H plus OH is water.
Right.
If you think about it, because H is one H and OH is another oxygen and another hydrogen, so it's H2O, right?
Right.
Yeah, but then the sodium chloride kind of shows you there, because the sodium moved to the chlorine instead of the hydroxide, and the hydrogen moved to the hydroxide instead of the chlorine. So there you go. All right, this next one, this one you can tell, I'm sure.
Composed.
Yes, it is. No, actually, it's decomposing, right?
Yeah.
Yeah, decomposition. Okay, next one after that. Can you tell what that one is? These are easy. I think so. I think these are easy.
Combustion.
Combustion, that's right. See, I told you these are easier to me because you can actually see them.
And this one is a combustion.
You're correct. And the last one? Well, not the last one.
Uh,
What is going on in that one?
mm.
Look closely.
So is it a double?
Nope.
It's a synthesis.
Mm-hmm. Why is it a synthesis? How many products do we have? One, right? There's
One.
no plus. There's no plus after the H2.
Right.
All right. And this last one, this one you'll be able to guess, I think, because you're good at these.
Uh, so did they get married or did they get divorced?
These are actually swinging.
Like,
I don't know what they're doing. They're cheating.
there's a lot of cheating going on.
Yeah, double replacement.
So that's a double.
Yeah, see how the NO3 is with the silver here, but it's with the sodium here?
Mm-hmm.
And then the chlorine is with the sodium here, but with the silver on the other side.
Right.
That's how you know it's a double. I know. I like the way you said that they get married, or they get divorced. Either one. They're gonna get divorced after what they're doing. Yep. All right, so there you go. And you know, you're always welcome to go back and look at these again, and make sure that you know what you're doing with them, because that's part of the thing. But that's basically it for today, unless you want me to show you the one thing that I think you should look at. One more thing. It's an important part of this, and there is a thing called balancing equation tutorial.
Mm-hmm.
But we can look at it next time too. But I just want you to know that it exists, and it Actually, all the little tips I gave you, they're in here. Everyone.
Okay.
Except for the combustion one. That one they don't use. They actually do the half and they say, then you're gonna have to double it. I'm like, that is so stupid.
Right.
See how they do that here? See? They
Mhm.
do the half and then they double everybody, which all you had to do was check the 6 is a 3, therefore double everybody to begin with. See?
Right.
Easier. Like I said, I actually ended up knowing this because of how many times I've done this, that
Mhm.
I realized that that's the best way to do it, is to actually check the age.
Mhm.
And see, it never fails. The age is odd when you divide it by 2, then you put a 2. Always.
Right.
There's another combustion in here somewhere, I think. No, there isn't. Oh yeah, there is, right there. Oh, well, it's backwards. Actually, they did this one backwards. Yeah. No, they actually, no, they didn't do it backwards because there's no water. Never mind. Yeah, there's no other. There's magnesium. Oh, yeah, there's one. See, again, check this one. You're going to end up having to put a 2. No, you're not, because it is 8. So no 2 on that one. And we'll, like I said, we'll do more of these later next time, but just wanted you to see that this is here.
Okay.
And it might be a good thing for you to read it and see what it says about the tips, because there are some tips and some no-nos, but you know the no-nos already. So
Right.
tips are right here. See, a summary right there. This is the tips.
And then we just do the chemical equation bonus.
Yeah. Mhm.
Okay.
Actually, I think you can do both chemical equation and chemical reactions now.
Okay.
They should be open, but I'll check if they're not.